So we're going to pick up Chapter 2 with looking at system analysis. It's important to study systems to look at how matter and energy flow in the environment. So an open system is when there's exchanges of matter or energy occur across system boundaries, and that's most cases that we'll look at. And a closed system is when matter and energy exchanges across the system boundaries do not occur. It's pretty rare. There's some cave systems that have closed systems. The Earth is an open system with respect to energy, because energy is always coming in. And it's closed with respect to matter, although we do have a little bit of matter added to our Earth. It's pretty negligible. And so this is our looking at energy and matter in terms of it being an open system and a closed system. It's important to look at a whole system because you need to include all the interactions between the components. So we're going to start by looking at inputs, which are additions to any given system, and outputs, which are losses to a system. And if we're doing systems analysis, it's the process by which you determine the inputs, the outputs, and the changes under various conditions. So we can end up with something that's in steady state. Steady state is when the inputs equal the outputs, so the system is not changing over time. The example is this bucket. The input is 1 liter per second, and the output is 1 liter per second. So even though we have all these little holes leaking out, the bucket is at a steady state because the level that it's filled stays the same as long as the water going in is equal to the water going out. Most systems are in a steady state. Another example, a natural example, is the amount of water that enters the atmosphere by evaporation is usually equal to the precipitation. Oceans are usually in a steady state, but with global warming, that may not be the case as much as it used to be. So feedback is the adjustments in input or output rates, which means that the results feed back into the system and change the rate of that process. So looking at what's called a negative and a positive feedback loop is kind of an important thing for this unit. The examples are right there drawn, and we'll look at them specifically. But a negative feedback loop is when a system responds to a change by returning to its original state. Essentially, it resists change. Now, I want you to realize that a negative feedback loop is not bad, and a positive feedback loop is not good. It's not bad or good in any way. It's just what it does. So a negative feedback loop is when a system responds to a change by returning to its original state. If we look at the example on the left below, we have a lake level, and the level of the lake drops. As the level of the lake drops, it has reduced surface area. Because of the reduced surface area, there's less evaporation. Because there's less evaporation, the level rises. And so it sort of takes care of itself and helps keep, response that lake back to the same level. Whereas a positive feedback loop, we look at something like we have a population increase, so we have more births. Because we have more births, the population increases. Because the population increases, we have more births. Because we have more births, the population increases. It is positively feeding back into itself and causing the change to be amplified or magnified. So if you think about negative feedback loop, if you have something to put in your notes, a negative feedback loop resists change, whereas a positive feedback loop amplifies change. So looking at environmental conditions that might vary among systems. So we're looking at natural systems. Environmental conditions that can vary are temperature, precipitation, or soil composition. Natural systems, what can live and grow there, the difference in environmental conditions are temperature, soil composition, results in geographic variation among systems, passage of time. Humans affect natural systems and what can live and grow there. In the response to changing conditions, things like migrations, extinctions, evolutions of new species are all the ways we respond to changes. And then your book closes at the end with managing environmental systems in the Florida Everglades. So the Everglades, which means river of grass, you can sort of see that from the picture there, and it's home to many threatened or endangered species. Due to rapid population growth in Florida, there was a need for water and farmland to help give water and food to these people and water to different crops. And so 30% less water was sent to the Everglades or diverted to the Everglades. And the water that was there had increased nutrients, increased phosphorus, particularly from agriculture. In 2000, the comprehensive Everglades restoration plan was enacted, and it had 3 parts, 3 goals to the project. The first goal was to increase the water flow. So in order to increase the water flow, they removed 240 miles of levees, canals, and water conservation and water storage, and purchased land from U.S. Sugar Corporation. So they removed a bunch of things that block the water, such as the levees and canals, and then they increased the water conservation and storage in order to increase that water flow through the Everglades. The second goal was to reduce water pollution. So the ways they went about that was to improve waste treatment, and then to place restrictions on the use of agricultural chemicals. And then they built also marshes to help filter the water before it made its way into the Everglades. And then the third goal was an adaptive management plan. Essentially, have a strategy that is flexible so it can be modified, because this is a highly complex system, and that's sort of the goal of this unit, to realize that these are not in isolation, and we're looking at highly complicated systems. And that's the end of Chapter 2 for this unit.